Okay, and all right, so let's get started. So Soledad Villar is an assistant professor of applied mathematics and statistics at Johns Hopkins University. Currently, she is a visiting researcher at Apple Research in Paris, and she was born and raised in Montevideo, Uruguay. And today she's going to be telling us about exploiting symmetries in machine learning models. And we're very excited that you accepted our invitation to present at the AI4Science seminar. So looking forward to your talk.
Thank you, Rocio, for the invitation. And please, if you have questions, please ask. We can make this interactive, and I'm happy to talk more about things that you may be more interested in and less about things that you don't. Okay, so the idea of this talk is to explain how one can exploit symmetries in machine learning models and why one may want to do it. So as a motivation, I may start saying that you're all doing AI4Science, so you're very familiar with deep learning models, and you know that these deep learning models are very over-parameterized, meaning that you have way more parameters than data points sometimes, and the function class that you're considering is very expressive, so you can express many functions in the class that can fit the data perfectly. So which one is the right function that you want to use for your model? And so there's a notion of inductive bias, which basically means that it's a way to understand your class of functions or the parameterization of the class of functions, so that when you do local optimization, like stochastic gradient descent or ADAM, you converge to something, some function in the hypothesis class that not only fits the data, the training data, but also it generalizes outside the training data, so to unseen held out data. So how can you do that? And so there's a lot of design choices that people do in the how do you parameterize different classes of functions that are useful for machine learning. And so different kind of architectures that had appeared in the past 15 years have some properties that are not very well necessarily explicit, but they do somehow, you can identify that there's some symmetries of the data or of the problem that are being exploited in the design of the architecture, either implicitly or explicitly. So for instance, convolutional neural networks are equivariant or approximately equivariant with respect to translations in the images by applying the same filter in different parts of the image. Recurrent neural networks exploit some form of time translation symmetry by using the same recurrent units in the test and in text data. Graph neural networks are especially designed to satisfy the graph permutation symmetries. And then transformers are very flexible, and they're designed in a way that are symmetric with respect to permutations, but also they can be adapted to incorporate other symmetries as well. So one can say that these deep learning architectures that have good inductive biases have some symmetries in mind in the design. And so this is what you were discussing earlier before we started the talk, that there's one way that physicists think about symmetries, and they divide the symmetries in the two classes of symmetries, the ones that are passive symmetries and the ones that are active symmetries. So the passive symmetries are the ones that have to do with the fact that if you have a physical object, there's not a unique way to write it mathematically. And for instance, if I have a physical system, I can express it in different coordinate systems, or I can use different units to express their mass, like either kilograms or pounds. And so if I do a transformation in the units, the system doesn't really see this transformation, and therefore it doesn't care. So the machine learning models that one designs have to be equivariant with respect to these coordinate transformations that can be units or coordinates or gauges in the cases of manifolds. And there's also the active symmetries that are actually observed regularities of the physics. And by Noether theorems, they're related with conservation laws. Conservation of energy is related with time translation symmetry. Conservation of momentum is related with translation symmetry, etc. And so one of them is just like coming from the mathematical choice, and the other one is coming from the actual physics. And the claim is that if we're doing machine learning for data science or for science, like you're doing here, it would be a good idea to make the models to be respecting of these symmetries, because then that would give you a model that is consistent with the thing that you want to that you want to learn. And so these symmetries are typically expressed mathematically in terms of invariances and equivariances. Basically, if you have a group G, so say, for instance, discrete rotations or rotations acting on your data set, you say that a function is invariant if you apply the group transformation to your input and the function doesn't change. So for instance, here we have this classification problem of this image. And if I apply a transformation like a discrete rotation, then the classifier doesn't change, just invariant with respect to these discrete rotations or maybe reflections. And it's equivariant if you transform the input, then the output transforms in by the same group action, or well, by the same group. Maybe the action in the input and the output can be different. So say here we have this particle simulation and we're predicting what will happen in the future. If I apply rotation to my particles, then the prediction should rotate in the same way. And so in equivariant machine learning, what one does is it takes the hypothesis class. So it's some hypothesis class that you're doing the optimization, and it has the property that for every choice of the parameters, the function that you obtain obeys the symmetry. So for every theta that is a valid possible parameterization of my solution, f theta is invariant or equivariant. And so the question is like, how can we, so this is a hard constraint, and how do we parameterize the class of functions so that every function in the hypothesis class satisfies these properties? And it depends on the group, for instance. So one example that is very common these days in machine learning is graph learning. Like when you look at graph neural networks, these graph neural networks are designed so that they are equivariant with respect to permutations. And this is a passive symmetry in the sense that this is a graph, and then I can write this graph as an adjacency matrix, and the choice of adjacency matrix is not unique. So I can write it in this form, or I can write it in that form, and these are equivalent. So these are two equivalent representations of the same object. And so if I'm learning a function of the matrix, then this function needs to be independent of the way I use to represent the graph. So this mathematically, you can write it as like, say I'm learning a node embedding, is a function that takes this graph and outputs an embedding for each node. So if you see it as a function of the adjacency matrix, it has to have the property that if I permute rows and columns, then the output embedding has the same permutation in the output. And this is how you write it. And so all graph neural networks that people use, message passing, graph convolutions, and more complicated forms of graph neural networks satisfy this property. And so there's a lot of questions in graph neural networks of like, how can you efficiently parameterize the space of invariant or equivariant functions with respect to this group action so that you get something that is expressive enough so that you can write interesting functions there, but also is a parameterization that is scalable, like you don't have exponentially large number of parameters. And that's a very large area of research where people study the expressive power of graph or message passing neural networks or graph neural networks, etc. I'm not going to go into the details of that, but I'm happy to discuss it afterwards if you want, if that's something that interests you. I know that the graph neural networks have a lot of applications to scientific domains as well. But today I'm going to focus on other forms of equivariant machine learning that do not have to do with graphs necessarily. For instance, equivariant machine learning on images or in particle systems. And you mentioned that you are interested in problems like protein folding. So that's the AlphaFold, for instance, includes some equivariant machine learning components in the architectures. And this is our equivariance with respect to rotation. Say, like, if you have a protein, then you want to do a prediction of how it will fold. If you take that protein and you rotate it, then the prediction should rotate in the same way. So it should be equivariant with respect to rotations, say. So in this talk, I will mostly focus on explain how to implement equivariant models on particle systems. So rotations, translations, Lorentz transformations and permutations, and scalings, which have to do with these units that I told you earlier. And then I will explain a little bit of how can we implement equivariant functions on scalar, vector, and tensor images. And then I have a few applications with collaborators in cosmology and in vegetation dynamics. And I can explain a little bit of that as well. So we said before that we want to do machine learning and in functions, in class of functions that are invariant or equivariant with respect to some group action. So how do people do that in practice? So the most common way to do it is through data augmentation. So you transform your data set and add more training points that have to do with like applying the group action to your input data, and include that. There's also some way of implementing symmetries or promoting symmetries by doing some loss function penalties. This has to do with the connection between conservation laws and symmetries in physical systems. But what I'm going to focus on today is how to do it through architectural design. So how can we restrict the class of functions to satisfy the symmetries? And so there's many ways that people do this. So weight sharing is, I guess, the one way of saying it. For instance, has to do with like the way people implement graphical networks through message passing using the same message function for every node. You can see this as like a weight sharing architecture, and that implements a permutation symmetry. There's a way that is done via irreducible representations. I will maybe discuss it a little bit, but not a lot, unless you ask me questions. Then symmetries as constraints, and then invariant theory, which is the things that I'm working on. So let's start with like a very general way to do this using like a generalization, not a generalization, but like just how can you modify a classical MLP to be equivariant. So let's start with that. So this you can see in papers by Condor, and Maron also has a paper that explains how to do this. The idea is, say that you have a feed-forward neural network, an MLP. And so this is a composition of linear layers with nonlinear activation functions. And so if you want to make it equivariant, what you can do is you can try to make the linear layers equivariant with respect to the group action. And then if you do that, then you need to see how you modify the nonlinear activation function in order to preserve the symmetry. So, for instance, if the action is permutations, then any nonlinear activation function will preserve the symmetry. But if the action is more complicated, then it's harder. So basically, that's the idea. So you take the linear functions, and then you say, well, now my linear functions need to be restricted to the linear equivariant functions, which is a linear subspace of the linear functions. However, that has the issue that it can be too restrictive. Like, there are not that many linear functions that are equivariant with respect to group actions. So think about, like, if you're looking for a linear function that preserves rotations, then you probably just only have just the identity or negative identity. So this is not very expressive. So so the way they solve this issue is by extending this architecture. So instead of just working on inputs, vector inputs, they extend it to tensors. And so the idea is that now, instead of taking a vector input, I'm going to take a tensor rd to the k. And so the way the group acts on this tensor is by acting in each of the like dimensions of the tensor independently, like this. And then they look at the linear equivariant functions in this tensor space. And so that is basically saying, well, it's kind of generalizing it so that instead of just having the linear equivariant functions, you have something like the equivariant polynomials of degree, the order of the tensor. That's basically the idea. And in order to parameterize these functions, is a little bit complicated because that's where they use the representation theory. So they say, well, how do we parameterize the equivariant functions from this tensor space to this tensor space? They use techniques from representation theory to do that. And they need to compute something called the Clebsch-Gordon coefficients. I have a few slides that explain this, but I would decide to skip it. And if you have questions, we can discuss it, or now or later. But basically, this is what people do for with like these n-body networks or these E3 CNNs, like for molecules, for molecule dynamics. This is how it's implemented in general. Just they do an architecture that looks like this. They change the linear layers to be linear in tensors, and then they parameterize the equivariant linear in tensors by using Schur's lemma, irreducible representations, and Clebsch-Gordon coefficients. And there's very nice tools that does it. There's a like, if you look at Tess Smith at MIT, she has a E3 CNN package, and they implement this, and they have applications to molecular dynamics. E3NN. Okay, got it. Sorry. Thanks. Okay. So if you already know this and and I'm going too slow, please let me know and I can step up. So another way to implement invariant models or equivariant models is using techniques from invariant theory, like very classic mathematical tools from like the 50s and the 40s. Basically, the idea is the following. There's something called the first fundamental theorem of invariant theory that characterizes what are the invariant polynomials with respect to several group actions, and that is something that you can use to parameterize machine learning models. So the goal here is going to be the following. So we have, say, this point cloud, and we want to predict the positions and velocities of this point cloud after a certain time, and that's going to be an equivariant function. So I'm going to start with just predicting a scalar value, which is maybe the energy of this point cloud. So if I have a function that takes n points in RD and outputs a real value, and this function is invariant with respect to the action of OD, which is the reflections and rotations, in the sense that if I take a matrix in an OD, so an orthogonal matrix, and I apply the same transformation to all of my inputs, so I rotate all the points in the point cloud, then the function doesn't change, right? So this is the action. And so the theorem says that a function is invariant with respect to this action if and only if you can write it as a function of the inner products of these input vectors. So this is what I write here. F of B1 through Bn is invariant if and only if F can be written as an F tilde of the pairwise inner products of my vectors. So basically, I just like start with these n vectors in RD. I construct my features that are going to be n square inner products, and any function that is invariant factors through this feature map. This is what the fundamental theorem of invariant functions for OD tells you. And the same fundamental, there's a similar fundamental theorem for invariant functions that applies to SOD, so just rotations. and the Lorentz group and the symplectic group. This is something that can be seen in generality. And basically that's how you can parameterize the invariant functions. So one question that people ask a lot is like, you go from ND to N squared, so you're kind of like exploding the number of features that you need. But actually, there's some techniques that allow you to reduce the number of features that you use and have the same expressive power. So now,
can I ask a question here?
Mm-hmm.
So this seems awfully similar to the notion of kernel methods, right? This is a connection here to kernel methods. Maybe can you comment a bit on this?
Yeah, so you can say that there exists a kernel that characterizes all the invariant functions, and that kernel is the inner products. So if you look at, for instance, another group like the Lorentz group, then the kernel that you will need to use is the Minkowski inner product, defined in a different way. So basically, if you can write the invariance as a function of pairs of vectors, which you can do in the case that the group is defined as a stabilizer of a bilinear form. So here the bilinear form is the inner product. Then the invariants are written as like a function of this bilinear form of these two elements, and then that characterizes the space of invariant polynomials, or the invariant functions.
Gotcha.
Yeah. So actually, when you do kernel methods, depending on the kernel that you choose, you may be obtaining functions that are invariant with respect to a certain group. So here, basically, what we are doing is just understanding, using these very classical things to understand, given the group, what is the kernel, and in some cases, you can have a matching, and then like you can have that the group is equivalent to a kernel. So in some cases, that's not the case. So for instance, I don't know if I have it here. Yeah, I have it here. I wasn't like, I have a like hidden slide here. So if you look at SOD, so it's not just it's not the orthogonal group, but it's just the rotations. So the determinant one orthogonal matrices. The invariants for that action are not just the inner products, but also the inner products and the subdeterminants of D by D submatrices of your matrix of vectors. So in that case, if you want to have a kernel that is like SOD invariant, that the kernel will not be able to, like, if it's a function of two vectors, it won't be able to like recover the SOD invariant functions, because the invariance will require you to have D vectors. Does that make sense?
Yeah.
Because you will need to take subdeterminant.
Yeah, because you need the sign basically of the determinant to determine the parity, right? So
yeah. So here, and that's for SOD, and then for the Lorentz, you can use this inner product that is called the Minkowski inner product, that you look at these vectors in space-time, and then the inner product takes the product of the time component minus the inner product of the space components. And so if you use a kernel based on this inner product, then what you recover are the invariant functions with respect to the Lorentz transformations. Yeah. So then you can use these techniques to express the equivariant functions as well. And so the way to explain this in simple terms is the following: is that if you have a function that takes these n vectors in Rd and outputs a vector in Rd, this function is OD equivariant if and only if you can write it as a linear combination of your input vectors times, well, I guess these are the input vectors, times a coefficient functions, and these coefficient functions are going to be all the invariant scalar functions, so functions of the inner products as we had before. So this is something that you can just prove by hand. For this example, is very simple. If you want to prove it for other groups, you can also do it. But there is like a general construction in invariant theory that allows you to go from invariance of copies of a space to equivariant functions. And I have a slide later on, but it's basically just like an invariant theory construction that allows you to go from the invariant functions to the equivariant functions. And so you can use the notion of the invariance to parameterize the equivariant functions. And it's very simple, and you can just define an architecture of these terms, in these terms. So you take your input vectors, you construct your scalar features or your kernel, as you mentioned, and then you learn these invariant functions, which are going to be your coefficients, and the output is just going to be a linear combination of your input vectors with these coefficient functions that you just learned with like MLPs or something like that. And with this architecture, you make sure that every function that you can express is equivariant, and every equivariant function can be expressed in these terms under some assumptions of like, if these things can be universal, say.
Yeah, so I have another, sorry for hijacking the conversation. So the discussion about sort of the parity invariance that you had above, I think you expressed, I guess you can also express this instead of using determinants as with cross products, right? No, then you would have to have a norm of a cross product, then they would essentially be back to having a determinant. So that's
yeah.
Okay.
So these invariant features with the determinants. Yeah, so if you look at the cross products, so this theorem that I have here doesn't hold for SOD, because this is telling you that if you have an OD equivariant function, it lies on the spans of the inputs. But for SOD equivariant functions, they don't need to lie on the span of the inputs, because you can take two vectors and the cross product is an SOD equivariant, but doesn't lie on the span of the inputs. So actually, the theory of how to go from invariant functions to equivariant functions explains that case as well. And we have a paper where we explain that example. I can share with you if you want.
Yeah, that would be great. Yeah, thanks.
Yeah. But basically, yeah, it's an algebraic construction that allows you to see that you can obtain the invariant functions by taking gradients. Sorry, the opposite. You can obtain the equivariant functions by taking gradients of the invariant functions. So in this case, taking gradients of the invariant functions, since the invariant functions are just inner products, then the gradients are just like a linear function, right? But in the other case, where your invariants include determinants, that taking the gradients of the determinants allow you something more complicated to show up. But yes, that's basically the idea. Mm-hmm. Okay. So this can be very easily adapted to, say, translation symmetry by just like, say, removing, like subtracting the center of mass and then adding the center of mass and things like that. The permutation invariance is like a little bit more complicated. But there is a formulation that has to do with permutation invariant and OD invariance. And this formulation that I have here is actually, you can implement it with message passing, but I think that it's possible to improve the formulation in a way that is more clear or more easy to implement. So the idea is that if you have an invariant function that is also the invariant, then the function can be written as also OD equivariant, sorry. The function can be written as like a linear combination of your input vectors with some coefficient functions where the function is the same for every VI, but it's a function of VI and the rest of the vectors. So it's kind of like, this looks like a message passing because the function of me and everyone else, that's my coefficient function. So you can implement it in something like a graph neural network form. So this slide basically is to mention how do you go from invariance to equivariance. And the idea of this is my postdoc, Ben Bloom-Smith. He is an invariant theorist. He did his PhD in invariant theory, and now he's working with me on more machine learning-like things. So basically, there is a very old literature in invariant theory that explains an algebraic construction of equivariant functions from invariants. And basically the idea is that if you have a group acting on a space V and acting on space W, it can also act on the maps between V and W, and the invariant functions, the equivariant functions from V to W can be obtained from the invariant functions on the space of maps. That's basically the idea. So, and so knowing the invariant maps from V to times W star to R, so this is the dual, but in the case of the orthogonal group, we can say that they are the same. The knowledge of the invariance from the product space to R gives you understanding of the knowledge of the equivariant map from V to W. That's the trick, and the trick is basically by taking the gradient. And maybe I can share with you the references for that. So I was thinking in presenting a few examples, and maybe also I don't know how we are on time. We have like maybe 15 more minutes.
Yeah, we have about, you can talk 20 more minutes, and then we leave some minutes for discussions.
Great. So I'm gonna start with the simplest example, which is a double spring with like a double pendulum with springs. So this is just a simulation that I took from the. Yeah, someone asked me in the chat, which kind of spaces are V and W? So V and W could be any space. So in our example, we have like RD to the N to RD. And so basically the idea is that equivariant maps, say H from RD to the N to RD is equivariant. Then we can take a function F from RD to the N times RD star to R, which is invariant, which is basically, I'm gonna write it down just so that it's simpler. So basically, if I have an equivariant function, and then I take if I have like F of V1 to Vn, I apply, H of V1 to Vn. So let me write it here, just 1 second. So F of V1, Vn, V star, this is the extra guy that I have here, is going to be equal to my equivariant function evaluated in my original vectors, inner product, the V star. So here, since we are acting with the orthogonal group, then the orthogonal group acts the same in the space and in the dual. So you can identify this star with just RD. So I take n vectors in RD, and then given an equivariant function that takes n vectors in RD and outputs a vector in RD, I can construct an invariant function, which is just taking the equivariant function and then taking the inner product with the last thing. So if this function is equivariant, then this inner product is invariant. Because if I take a rotation to everything, RV1, RVN, RV star, then when I apply the equivariant function, what I obtained is going to be RH of V1, Vn, just because it's equivariant. And then when I take the inner product with RV star, then the R cancel out. So that's more or less the construction that allows you to go from an equivariant function to from an invariant function to an equivariant function. So then the question is like, if I have this invariant function, how do I obtain the equivariant function h? And then here, what you can do is just like divide by v star, which is the same as taking the derivative of this function with respect to the last component. Okay, maybe I should have added that to the slides, but yeah. Thank you for
thank you. Sorry, I just wanted to know. So I understand now that V&W needs to be vector spaces, right?
Vector spaces, yeah. Yeah.
Okay. Thank you very much. This is very useful.
Yeah. So this says, okay, if I have an invariant function of these terms, maybe all these like commutative diagrams were not that useful as this. If I have an invariant function of these things and I take the derivative with respect to the last component, then I obtain an equivariant function, this. Or maybe if I divide by v star, then I obtain this function that is equivariant. Okay. So now I'm going to explain some numerical experiments that I think are quite interesting. So in this case, we have this double pendulum with springs, and the data is the positions and the momentums of the masses. Maybe you have some masses, some spring constant, and some lengths of the spring. And the problem is to predict the dynamics. So this is a Hamiltonian system. The kinetic energy plus the potential energy are conserved. That's a Hamiltonian. And so our goal is to predict the dynamics. So say, given this data, positions, velocity, positions, momentums, and I'm gonna add the gravity vector as an input to my problem in order to make it equivariant, because this problem is not equivariant with respect to O3. But if I say that the gravity vector is an input to my machine learning model, then it will be equivariant with respect to O3, because the way I write the potential energy has inner products with the gravity vector. So okay, if I add the gravity vector as an input, then this is kind of like when I do a rotation to my inputs, is basically a change of coordinates. So it's kind of like a passive symmetry. So if you add that as an input, even though it's constant, then you can use O3 equivariant models. And these O3 equivariant models, as we saw, they're very easy to implement because you can write it in terms of the inner products. So that's one advantage that one could use in writing in a way that is coordinate free in some sense. So I think that's an interesting point. And then how do you learn the dynamics? Well, we can write two computational approaches. One that just learns a differential equation using a neural ODE, and basically just learn like a function, which is the derivative of your thing that you want to learn with respect to time. And this is going to be a equivariant vector function, which is R3 to the 4, because you want to learn 4 things. So it's an equivariant vector function, and then you can just use a neural ODE to solve that, which is you can parameterize the class of functions using the architecture that I explained earlier. Or you can impose another symmetry, which is a Hamiltonian symmetry, because we know that the system is Hamiltonian. And the way you can implement that is by learning a scalar function, which is going to be the Hamiltonian, and using a symplectic integrator to integrate the dynamics. And then what you can obtain is that of course, the more symmetries that you impose to your problem, the smaller the generalization error is. And that's something that also you can prove mathematically in terms of dimensionality reduction. But numerically, it works. And you can see, well, the more symmetries. So here, this is the largest group that we impose, but then there's smaller subgroups that you can impose. And we use the work by Mark Finzi that implemented all these subgroups for this specific problem. And this is an MLP where it imposes no symmetries. And then the comparison is with the neural ODE which does not impose the Hamiltonian symmetry, and then these HNNs, Hamiltonian neural networks that impose the Hamiltonian symmetry. And it works very well. So I guess that's the message. The more symmetries you impose, and you know this is a physical problem, it has these symmetries. So yeah, the more symmetries you impose, the better, the smaller the generalization error will be. And then the other symmetry that we used as well is the symmetries that has to do with the units symmetries, because we're learning a potential like a Hamiltonian based on potential energy and kinetic energy, and energy has units, kilogram meter square divided by second square. And so if I do a transformation where I transform everything that has units of kilograms to pounds, then that is the scaling, and then the predictions should scale in that way. So it should be invariant. It should be equivariant with respect to scalings that take that. So for instance, if I take everything that has units of kilograms, I multiply it by 5, then the prediction should multiply by 5. If I take everything that has units of meters and multiply it by 10, then the prediction should multiply by 100, just because of the units of the things. And that you can write it as a group action, and you can use classical ideas from dimensional analysis to implement a machine learning model that respects these symmetries as well. So the idea is using this called like Buckingham Pi theorem that tells you that if you have your input features, which have units, then you can find a map that takes this into dimensionless features. So just like cancel, like a map that takes your original features and then makes them dimensionless. You can do the learning on this like dimensionless space, and then you can multiply it by a fixed scaling and obtain the output, which has the right dimensions. And if you see, like, this is something that people do in machine learning, like not in machine learning, but just like in numerical methods for science. That's something that everyone does. It's just like it's obvious that when you're looking at a solver, a PD solver for some physical problem, like a turbulence problem, everyone does a transformation that makes it dimensionless, and that's the learning in the dimensionless space. So this is nothing new, but it's just like if you're doing machine learning, you should also implement these symmetries in the machine learning models, I believe, but I don't know. It may be harder to implement, because when you construct this map from the original features to the dimensionless features, you may have to divide things. The transformations include like taking quotients. So for instance, in order to make something dimensionless, I would take the mass 1 divided by mass 2, etc. And so if things are not well conditioned, then you may have numerical instability, because you have to take divisions. So that's something that needs to be done carefully. And we not only observe that this works, but also that it allows you to do like out of distribution generalization. So if you do a transformation of your input data so that it makes like a scaling of the input data, you can maybe still perform well if there exists a scaling of the training data that is close to the new data that you give it. I don't know, I didn't explain that right, but just saying that it allows you to generalize to other domains that you may have not seen, just because when you apply this group action to the original domain, you can reach out farther out. That's the point. So I have a question in the chat that says, there is a tradition in ML to do data whitening prior to modeling. I guess this is related. I think so, but I think that whitening is typically done in a dimensionless space, right?
I guess you just take a arbitrary feature space, right? And then where you don't necessarily know what the dimensions are, the data will always have some sort of features, right? Also some sort of units, may and may not be well-defined physical units, but to remove you do widening to remove sort of arbitrary scales, that might be unimportant for learning, right? And so in that sense, I guess it's to some extent related. Maybe this is a more general concept you're talking about.
I see. Yeah. I don't know, but maybe there is a way of thinking about the connection between those things. Yeah. So I just want to mention that one application of these models are to cosmology. And so my collaborator David Hogg and his student Kate Story-Fisher have been working on applying these scalar-based regressions to some problems in cosmology. And basically the idea is that they have like two kinds of simulations. One of them that are called hydrodynamic simulations that are very expensive to produce, and other ones that are called dark matter only simulations that are cheaper. And so what they want to do is they want to predict properties of the expensive simulations using the cheaper simulations using machine learning. And so if they want to do this prediction, then this prediction makes sense to make it equivariant or invariant with respect to rotations, OD transformations, just because of how the problem is defined. And so what they do is they do some scalar features on this looks like point clouds. Their data looks like point clouds, these simulations. So they do some form of binning of the point clouds, and they take features that are invariant scalars, and also they take features that are basically like tensor products that are equivariant, tensor products of the different moments at the different bins. And they use these like geometric features based on this multiple expansion, and they do the regressions based on these features. And this is something that Kate is doing for her PhD thesis, and she is graduating soon. So if you're interested in talking with her, I think she can do a much better explanation than I do. And also, when you have this matrix constructed in an equivariant way, so you can take the spectrum of these matrices, and this spectrum, like the eigenvalues of these matrices, are going to be invariant, for instance, with respect to this group action. So that's very nice. Another application of this, and then they have some results of like how well these models perform with respect to some other baselines, but I don't think I want to go into that. Another example is in collaboration with Bianca Dumitrascu. Bianca is an assistant professor in Columbia Statistics. She just started growing her group there, and she works in computational biology. And she was interested in a problem that had to do with vegetation dynamics. So there's a model called the Ritker model that is used to model vegetation dynamics. And so she wants to do some regression and emulations with respect to these models. And also these vegetation dynamics models have a lot of parameters that have to do with like the rainfall and properties of the soil, etc. And all these parameters have units. So when we do the simulations and the regressions, it makes sense to do it in a dimensional space. Like this is like modeling a PDE and doing some regression. It makes sense to do it in a dimensional space, and then we can compare that. We gain a little bit. Oops, this is not okay. This, I don't know why it's broken, but yeah, we can gain a little bit by doing it in a dimensionless way versus a not dimensionless way. But it's not overwhelming, but it does produce some improvement. So I don't know how much time I have, probably not a lot, but I can just mention that my PhD student, Wilson Gregory, is working on writing some equivariant function models on vector and tensor images. And so in the classical example, with just images, basically the group that people consider, and this is based on the first paper that analyzed this is a paper by Taco Cohen and Max Welling, where they define these like convolutional CNNs that are invariant or with respect to discrete rotations. And so basically the idea that we have is to work on tensor and vector images that are motivated by scientific applications. Like, for instance, this is like an ocean dynamics problem, and this is a polarization problem. So at each pixel, you have a 2 tensor, and so it's basically like a generalization of equivariant convolutional networks to vector images, and it combines ideas from the classical equivariant convolutional networks from Cohen and Welling with the ideas from the scalars that I just told you, and how to go from invariant to equivariant using techniques from invariant theory. So basically it combines this CNNs that are invariant with tensor and vector images. They have many applications to scientific domains, and I know that you are interested in that in like different data that appears in different forms of scientific domains. So I'd be very happy to discuss how does your data look like, and if any of the techniques that we have could be applicable to that. So in the case of equivariant CNNs, basically they show, Taco Cohen and Max Welling show that in order for a CNN to be equivariant, then the filters that you have to use need to be symmetric. So if you want to do the same thing for invariant, equivariant functions on vectors and tensors, then you have to look at symmetric vector and tensor filters. And there's some questions about how to make this scalable, and basically these vector filters that are defined in this form, in the end, you can see them as discretizations of the classical curl operators or divergence operators that you can apply to vector fields. So you can, when you find a parametrization of, or like when you find a CNN that takes an input vector and an output vector field, you can maybe interpret like what it's doing to the field using in those terms. So for instance, some of these pseudo vector filters, you can see them as sharpening the image, versus some of the other ones, you can see them as a diffusion operator. So here, so this is your input, this looks like a diffusion of your vector field, and this looks like a sharpening of your vector field. That's basically how it looks like. So as a summary, I'm gonna end here, just say enforcing symmetries in machine learning models give you, I believe, the correct model assumptions and a small generalization error, better sample complexity out of distribution generalization. And we discussed a little bit about the symmetries in classical physics and how can we implement all equivariant functions with respect to orthogonal group and other simple E groups that show up in physics. How can we extend these ideas to units equivariance? How can we find an explicit translation between invariance and equivariance using invariant theory? And how can we extend these ideas to scalar, vector, and tensor images? And these are my references, and that's it. So yeah, the paper that I mentioned from the invariance to equivariance is this one, Bloom-Smith and me. It's on arXiv, and it's gonna show up in the notices of AMS. Okay.
All right, thank you so much, Soledad. Now we can open it up for questions. Oh, you have a lot of virtual applause, I think you can see.
Thanks.
If you would like to be unmuted, you can raise your hand, and I can let you ask a question. In the meantime, I had a question on that last part with the equivariant CNNs where you were showing all the different filters. Is the idea here to apply all the filters to your tensor image, or how do you choose which filters you're going to apply? I didn't quite understand.
Oh yeah. So for instance, the architecture can be seen as you have your input vector, your input image A, and then you take, for instance, a convolution with a filter C1, and then you take a tensor product with the same A convolved with the filter C2, and then maybe you convolve with another filter, and then maybe this gives you this here gives you a 2 tensor. So maybe you want to do a contraction using a Levi-Civita or using a regular contraction. And so say that this is your architecture, right? And so if this is your architecture, then what you can do is you can learn C1 and C2 and C3, like in a classical CNN, you learn these filters. And so, but the way you learn these filters is these filters are going to be a linear combination of your bases. So say that these are your bases.
Okay.
So you learn the coefficients of each of these filters in your machine learning model.
I see. Okay, that's cool. So it's going to be different then depending on the different applications and the different underlying symmetries then.
Yeah. So the way you define the product of like when you take the product of two images, then the product that you use in order for making equivariant is a tensor product. So the order of your image, of your tensor image, is going to grow. So you have to apply contractions at some point so that you don't use all your memory.
Right.
So there are different architectures that one can have, and yeah, I can share that with you if you want.
Yeah, that would be interesting.
And also Wilson is finishing this paper, and he's going to have his code on archive. And if that's something that you think that you may want to use it at some point, I will put you in contact with Wilson, and he can help you out.
Yeah, I'd be curious to learn a little bit more. I was going to ask if it wasn't published yet, right? It's a work in progress.
Yeah, but it's almost done. So
almost done. Okay. Okay. Any other questions from the audience? Seems seems not right now, but people ask lots of questions during your presentation. So now I want to just thank you again for speaking to our at our AI4Science seminar series. It was really a pleasure to have you, and I learned a lot, at least. Yeah, with that, yeah, you have lots of thanks in the chat as well.
Thank you.
Yeah. With that, then I guess we can conclude this seminar and see you all next month.
Okay.
Okay.